In this chapter, we're going to be looking at solving systems of linear equations and also using matrices, both to solve systems of equations and to use them in other applications. But we'll start this lesson with looking at systems of linear equations. So here's a system of equations with two variables. And we want to solve this system using a method called substitution. And in substitution, I solve one equation for one variable and then substitute that into the other equation. Usually it's easiest to use substitution if I have a variable like this y that has 1 for a coefficient. So I'm going to solve this equation for y. And I do that by moving the y over here to make it positive and moving the 1 back over here so that y is by itself. So this is now 2x minus 1 equals y. Now I'm going to take this expression for y and substitute it into this equation wherever there's a y. So I'll have 3x plus 2 times, I'm going to use my expression for y, 2x minus 1, and then equals 4. Okay, I need to clear these parentheses. So I've got 4x minus 2, and out here still the 3x and the 4. I'm going to move this constant over to the other side and combine terms here. So 3x and 4x is 7x is equal to 6. I divide by 7, and I get that x is equal to 6 over 7. Now when I'm solving systems, I have to always remember that when I get to this point, I'm not finished. I've got a value for x, but to solve the system, I need to have a value for y as well. So I'm going to take this value and put it back into one of these equations, and I'm going to use this one because the coefficients are smaller, and I think it'll be a little easier. So now I'm going to have 2 times 6 over 7, my value for x, minus y equals 1. Now I have 12 over 7 minus y, and I know I'm going to be combining this with the 1, so I'm just going to rewrite the 1 as 7 over 7. Once again, I'm going to bring the y this way. I'll bring the fraction this way. Make a little space here. So 12 sevenths minus 7 sevenths is going to be 5 sevenths is equal to y. So my solution is an ordered pair. And we start with the value we had for x, which was 6 over 7. And then the value for y, 5 over 7. Okay, so this is solving by substitution. And this is my solution set. Pause the video now and work your own system in checkpoint 1. Another method that's commonly used to solve a system of equations is called the addition method or the elimination method. because I add the two equations or multiples of them together to eliminate one variable, solve for the other one, and then put that back into one of the original equations. Let's see how this works. I've got 5x plus y equals 4, 3x plus 2y equals 1. And I want to use elimination. Okay, I can see in these equations that I have 2y here. So if I had negative 2y here, when I added the two equations, the y's would drop out and I would have only x's. So to accomplish that, I'm going to multiply this equation by negative 2 all the way across, and I'll just write the result down here. Negative 10x, negative 2y, and negative 2 times 4, negative 8. Don't forget to do this side. That's a common mistake. Now I'm going to add the two equations together. This gives me negative 7x. The 2y and the negative 2y cancel each other. I've got negative 8 plus 1, so negative 7 here. When I divide by negative 7, I see that x equals 1. Now I'm going to substitute that 1 back into one of these equations, and I'm going to use this one. So I've got 3 times 1 plus 2y equals 1. So I'm going to subtract 3 from both sides, and I have 2y equals negative 2. So then when I divide by 2, I have y equals negative 1. So my solution set is the ordered pair 1, negative 1. Pause the video now and work on checkpoint 2. Sometimes there's not an obvious approach to solving a system of equations. If I don't see an equation that's easy to solve for one variable, and I don't see any variables that have coefficients that are multiples of one another, I might have to multiply both equations by some number to arrange for one of the variables to be the same coefficient but different signs in each equation. So here's an equation or a system. 3x minus 4y equals 1. 2x plus 3y equals 12. And again, I don't see anything real obvious. I've got a 2 and a 3, so I could multiply this by 2 and this by negative 3. That would work. I've got a negative 4 and a 3, so I could multiply this by 3 and this by 4. That would also work. I'm going to take that first approach and multiply this equation by 2 and this equation by negative 3. So 2 times this is going to give me 6x minus 8y equals 2. Negative 3 times this, negative 6x minus 9y equals negative 36. Now I add the two equations together. The 6x's cancel out. I have negative 17y equals negative 34. When I divide by negative 17, I end up with y equals positive 2. Now I'll put positive 2 back into this equation. Gives me 2x plus 3 times 2 equals 12. Well, this is 6. So I have 2x plus 6 equals 12. Subtract 6 from both sides. And I get 2x equals 6. Divide by 2. And x equals 3. So the solution for my system would be 3, 2. Pause the video now and work on checkpoint 3. Sometimes when we attempt to solve a system of equations, we end up with all of the variables being canceled out, falling out together, and just either a true statement or a false statement. These systems are called either dependent systems or inconsistent systems, depending on whether we have a true statement or a false statement at the end. Let's take a look. So there's my two original equations. I'm going to multiply the first equation by 2, because I know that's going to make my 8's drop out. And now when I add these two equations together, 0x plus 0y equals 0. So I have 0 equals 0. When is it true that 0 equals 0? It's always true. Okay, so this is always true. And when we have a statement that's always true, 0 equals 0, then we say that the system is dependent and that it has infinite solutions. I can pick any value for x, and when I solve for y, it's always going to come out so that the x's and y's cancel out and has no effect on the solution. So this is called a dependent solution. Pause the video now and work on checkpoint 4. As I said earlier, sometimes we have a system where all the variables drop out, but we end up with a statement that's not true instead of a true statement like we did last time. So let's solve this system to see that. Okay, once again, I can see that these coefficients in the second equation are -2 times the ones in the first equation. So this is probably the easiest thing, is to multiply this by +2, which gives us 6x minus 4y equals 8. And when I add these together, I have 0x plus 0y equals 15. Well, 0x and 0y, that's just 0. When does 0 equal 15? It never does. So we say this is never true. And we say that is an inconsistent system. And again, that means that whatever value I pick for x or for y, I'm not going to be able to get a corresponding value for the other variable. So this is an inconsistent system. There is no solution to it. If you think about it graphically, where a system of equations is the point where the two lines intersect, the two lines described here will not intersect. They're parallel lines. So, inconsistent system. Pause the video now. Work on checkpoint 5. Our last example for this section is a word problem that shows an application where we might use a system of equations. And it reads like this. 800 people attended a basketball game and total ticket sales are $3,102. If adult tickets are $6 and student tickets are $3, how many adults and how many students attended the game? We don't have any equations given to us for this problem, so we'll have to formulate them ourselves. It's usually a good idea to, in a system like this where I have money, to write one equation that represents money and one equation that represents the quantity, in this case the number of fans at the game. So we know 800 people attended, and some number were adults and some number were students. It's also a good idea to write out here x equals adults and y equals students. You could also choose, maybe instead of x and y, choose a and s to remind you of what the variables stand for. So this equation represents the people. We need an equation to represent the money. $3,102 is equal to $6 for each adult plus $3 for each student. Solving this system is your checkpoint 6. Stop the video and work that out for yourself now.